finish the derivation of the minimum uncertainty wave packet that we started last time. So I think we were at the point where we consider the equality sign of the Schwarz inequality. So we were here. Maybe I can share whiteboard. So we have taken the equality sign of the Schwarz inequality because that would correspond to the minimum uncertainty. And this lambda is given by the overlap of beta and alpha divided by the overlap of beta with itself. So now we have not specified what the operator A and B are. So these are completely arbitrary. So we have here alpha we define to be delta A acting on some state F, and beta is delta B acting on state F, like this. So A and B are arbitrary operators, and we can then choose A, we choose this, A to be the momentum operator, and B to be the position operator. I think that's what I did in the notes, yes. So we have B minus some expectation value of the momentum operator is equal to lambda like so. So now we want to figure out what this state F is. So we want to look at it at the position representations. We want to know the function corresponding to this F. So we take projection to the position eigenvector. Should have put more space there. Okay. So now we can use what we have derived before. So we have xp acting on psi gives us, was it minus h bar d psi dx. So then we get minus h bar d dx minus p acting on fx here. So that's then equal to lambda. And so that just gives me x, because I can act it to the left. It becomes fx, that's it. So this is the equation that determines the minimum uncertainty wave packet. It's a first order differential equations, which is actually integrable, because if you look at this in the more general form, this is the same kind of integral as this one here is first order differential equation of this form. So this can be integrated because I can rewrite it like this. So that's minus c dx, and then I can integrate. So that then gives me the Gaussian. We do a little bit of algebra and work out this constant. You find that the function fx, the solution to this differential equation is given by exponential of x divided by h bar minus Gaussian here. It's like this. So it's a Gaussian. And C is just a normalization constant. And we have to determine what this lambda is. Move my things here. Okay. So the lambda, we see that we first recognize that for a Gaussian, this anti-commutator is equals to 0. So this is true for Gaussian. So you can check that. So then we get delta x, delta p. These are from the previous result. Just left with a 1/2 of that. So that is done from the uncertainty relation we get. I mean, from the commutator of x and p, we get then h bar upon 2. So that gives me the lambda. So that's, oops, should I erase this first? Okay, so that gives me the lambda. So the lambda is then just given by x delta p divided by so that is then just h bar divided by 2 times that expectation value of delta x squared. So this is then imaginary. And then we get the final result, which is what we want to derive. So that's 1 divided by. So I've left out all the algebra here, but that's, yeah, I think can be easily checked. X upon h bar minus the Gaussian. Where this omega squared is equal to the expectation value of delta x squared. So that's the derivation of the minimum uncertainty wave packet. So the solution is unique. So this is the only minimum uncertainty wave packet. Because there's only one solution to the differential equation. Okay, so that's the first part. So now I would like to start a new topic. So let me pick up a different file here. Yes. So now I would like to start with quantum dynamics. This is not something new. I think you have already known this subject before, but we will do this a somewhat different way. So we will follow the same kind of concept that we had with a translation operator, where the generator is given by the momentum operator. So we will treat time development of state by introducing what is called the time evolution operator or time development operator that kind of analogous to the translation operator in space. So here we are talking about translation in time, and the generator of this time evolution operator is given by the Hamiltonian, as we will see later. Okay, so let's start with kind of statement, the problem. So we want to know how a given initial state, an arbitrary given initial state, evolves in time under a certain potential. So we have a Hamiltonian, which is independent of time. So it's important that the Hamiltonian here is time independent. So we will consider the case of a time-dependent Hamiltonian later when we consider time-dependent perturbation theory. But here we consider an independent Hamiltonian. So if the initial state is an eigenstate of the Hamiltonian, then the time development of the state is quite simple. So we have state like this, initially at time t0, which is an eigenstate, the Hamiltonian with energy E. Well, then the time development is simply given by some phase factor, and it's an exponential, times the initial state, because it's an eigenstate. So then the expectation values of observable does not depend on the time. But this is not generally the case, because generally we would like to have some arbitrary initial state. So the question is then how we would do this. So we already know how to do this in a kind of conventional way. So if I have a state time, say t equal to 0, which is not necessarily an eigenstate of the Hamiltonian, then we can always expand this in the eigenstate of H of the Hamiltonian. And this is what this is just one here, and phi n is the eigenstate of H. So then the time development of this state is simply given by the time development of each of these eigenstates. So that's equal to minus t upon h power. I don't have enough. Okay, can write it here. Okay, so that's what we normally do. But we want to do this in a kind of different way, in a more abstract way, because it is more versatile, especially later when we do Feynman path integrals. We will use this other formulation using time evolution operator. It's a more versatile way of dealing with quantum dynamics, especially when we have many particles in a system, and it is a very useful tool of handling a time-dependent problem. So what we do is we introduce a time evolution operator this way here. Let's call it U. It's a function of t and t0. So we have some initial state at time t0 that can be any state, and then we just evolve it according to this time evolution operator. Then we get state at time t. So this is just like a definition of the time evolution operator. And we'll show that this time evolution operator is just given by this expression here. So for a time-independent Hamiltonian, the time evolution operator, the U, actually depends only on the time difference. So this is equal to 0. So this is kind of clear because the Hamiltonian is independent of time. So we can choose any time as our reference point. So it does not depend on the actual absolute value of t0. It's only in a time difference. And so we can also see here that it looks rather similar to what we have with a translation operator in space. So in the case of translation operator in space, we shift the position eigenvector by, say, delta x. So here we shift the state by delta t. So we can see that this time evolution operator also fulfills the properties that, or it has properties that it is unitary, because that's kind of by definition it's unitary, because we do not want to destroy particles on the probability. We do not want to violate probability conservation, and forms a group. So let's see what we mean by it. So we have unitarity. So we have U dagger. This operator. It's equal to 1. And then we have a group property. So group property, in this case, we can write this. Prime t0. So because the Hamiltonian is independent of time, so we have U delta 1, let's say, U delta 2. So that is equal to U delta 1 plus delta 2. Okay. So this is not necessarily the case if the Hamiltonian is time dependent. So that's you have to be careful there. But it is true here. So it actually forms a group. So we have then your unit element. Well, that's just given by this. So If we do not do anything, then we have just 1, because we go from t to t. And we also have an inverse. So that comes from the fact that we do this, that is just equal to u tt, because we connect that with time t0, and that is equal to 1. And then from the unitarity, we can see that the inverse of t0, say, is then given by the diagonal t0. So we can then use the same reasoning as we had before for the space translation. So it would imply that this time evolution operator, we consider t minus t0 equal to some delta, some dt, let's say. Then we have the infinitesimal time translation becomes 1 minus dt, like that, just like we had before with space translations. So this is the kind of form that fulfills the unitarity and the group properties. Same reasoning as we had before with the space translation. And we can show that this operator, the Hermitian operator, is actually just the Hamiltonian divided by h bar. Okay, so let's show that. I want to show that. We can show this rather straightforwardly using the Schrödinger equation, time-dependent Schrödinger equation. So we have time-dependent Schrödinger equation. So that's our starting point. So that we can write state in terms of the time evolution operator. We can put t0 here. Like this, but this state is arbitrary. We can start with any state, so that would imply that we have an equation for this operator, this time evolution operator, like that, because the state psi t0 is arbitrary, so you can choose any state you like. So then this must be true here. And the solution of this is quite simple. So that must be just some exponential. It's the minus sign here. Is 0. So in principle, we can have a constant multiplying it as its linear differential equation. But we have the boundary condition that u t0 is equal to 1. So then this c must be equal to 1. So we get rid of that, see that. So this is the solution to the time evolution operator. So you can see explicitly that it only depends on the time difference. So that's why this fulfills of the group properties, that you can multiply two of these and you get another time evolution operator with the sum of the time. And we can also, if we take this to be our dt, then we can just expand it, and we get h bar dt. So we say that this is just the thing we call omega. So in analogy to the translation space, then we say that this h is the generator of time translation. So the useful thing about this approach is that once we compute or calculate time evolution operator, we can just apply it to any initial state, because it does not depend on the initial state. So it's important to note that that this u here is independent of the initial state. It's just given by the Hamiltonian. As you can see this explicitly. So it's a nice tool because we can just apply to any initial state. Of course, the whole thing is just equivalent to the time-dependent Schrödinger equation. But the time-dependent Schrödinger equation can be kind of awkward to handle. So it is much nicer to work with this time evolution operator. So let's illustrate this a little bit with an example that we had in the beginning. So let's say that we start with arbitrary state. Sorry, so that's our initial state. Now we want to know, maybe I can put time, let's say 0 here. So that's the initial state. And we want to know how this state evolves in time. So then we just apply that time evolution operator on this state. And because t0 is equal to 0. So, and in general, when we want to compute the effect of an operator on an arbitrary state, so let's say we have an operator A acting on some arbitrary state, psi, let's say. So the general procedure is to insert the eigenstates of A. Yes? So we say that we have A like this, and then we insert complete. Okay, so we insert a complete set of states corresponding to the eigenstates of A. So it's equal to, let's say, n psi n, like that. So then go here. So that becomes then sum over n a n So, okay, so that's a general way of figuring out how an operator acts on a given state. So we can do the same here. So we insert here complete set of states, which are the eigenstates of H. No? So then you just get sum over n to the minus I n 1h bar t psi n psi n 0, which is what we had in the beginning. So we had this example. Okay, so that's the time operator. So it's a very general operator. So it can be used also to in the case when you have more than one particle. So if you have many particles in the system, you can define this, because this is defined with respect to some uh, mm, uh, state vectors. Since we have not specified how many particles we have, so these are general state vector. So the definition is true even when we have more than one particle in the system. And we will use this later when we do Feynman path integral. There is a question here. Yes, so the question is whether this type U is like a semigroup generated by H. Well, it's just a continuous group where you have T as your parameter. So this is a bit like the translation group, where the momentum is the generator. So you can say that this is a semigroup. Okay, so actually you do not need to worry about group here. So the next thing I would like to talk about, I think you probably also know this already, is a different way of viewing quantum dynamics. So we have the Schrödinger equation, time-dependent Schrödinger equations, and that is usually called the Schrödinger picture. But it's not the only way of looking at how system evolves in time. The Schrödinger picture, we put the emphasis on the state, on how the state evolves in time. But actually, one can shift the dynamics to the operators instead of the state. So if we do this, we have what we call the Heisenberg picture. Yeah? So the key point of relating the two pictures is that the expectation values of observables should not depend on how we view the system. Whether we work in the Schrödinger or in the Heisenberg picture should be identical, should be the same. So let's say that we have some states, time-dependent states, like this, and we want to compute the expectation value of some operator O. O can in principle also depend on time, but let's not put any time dependence here. So we just have some operator like momentum or some Hamiltonian or whatever. It just does not depend on time. So the expectation value of this operator then will be in this time-dependent state will of course depends on time. So it will be given by that by definition. So the value will change in time because the states change in time. But now we can use the fact that this states psi t, state psi t here is given by time development operator times some initial state psi 0. So we can choose the initial time to be 0 yes, because the Hamiltonian is time independent. So then if we plugged in here, we then get psi 0. So that will be the conjugate. Zero, like this. So now we can think of these as a unitary transformation of the operator O. So we can call it H on Heisenberg, which is now a function of time. And in the state, so this is then the Heisenberg state here, it now becomes independent of time. So Heisenberg state that is independent of time. So I can see explicitly here that nothing has been changed with respect to observables. So these are the observable physical quantity that you observe in your experiment. It should not depend on the picture. And so we have two ways of doing quantum dynamics here. So one way is Schrödinger picture here. So that's the Schrödinger picture. But we could also do this unitary transformation where we shift the time dependence or transfer the time dependence from the state to the operator. So now the operator is time dependent, whereas the state becomes static. It's just fixed at time t equal to 0. So by convention, the Heisenberg state and the Schrödinger state coincide at t equal to 0. So that's just a convention, which is a choice. Yes. So that the Heisenberg state, you can just write this like a time reverse state of the Schrödinger state. So that's the definition of the Heisenberg state. There's a plus sign here, and the exponential instead of minus. So that's like reversing the state back to time t equal to 0. So one wonders, why do we want to do this thing like this? These two are just equivalent. Like in many things in physics, there are many ways of doing the same thing, but some ways can be more convenient to use than the others. So depending on the problems, we can choose which way is more convenient. We cannot say this in general. So This all depends on the problem. Sometimes it is just more convenient to work with a Schrödinger picture, and sometimes it's more convenient to work with a Heisenberg picture, where you work with the operators instead of the state. In fact, when we do time-dependent perturbation theory later on, we find that there is another picture, which is called the Dirac picture or the interaction picture, which is much more suitable for handling perturbation theory problem. So there is no one particular picture that's perfect for everything. So that's a choice. Yes. So this is the Heisenberg picture, and as you know, for the Schrödinger picture, we have time-dependent Schrödinger equation for the states. So then we expect that we should have a time-dependent equation for the operators. And this can be rather straightforwardly obtained by simply taking the derivative of this operator with respect to time. So just following the definition of the operator, of this Heisenberg operator. So that, okay, so if I write down here, ht is equal to integral t, like that. So we just take the derivative of this. So then give us h bar times h, that brings down your Hamiltonian, and we have OH, so we just go click H. Like that, and then for the other one, I will get OH and I upon H like this. So this can be written as a commutator. Yeah. So that's the equation, the Heisenberg equation of motion. So well, one. So this equation of motion is actually also fulfilled when the Hamiltonian is time dependent. So we can, if we introduce or define the Heisenberg operator in this way, so this kind of illustrate also. Sorry, I should have start with that. Oops, what happened here? So I want to write the expectation value of t, this operator. So instead of using the explicit form of the time evolution operator, we can write the state in terms of the time development operator. Okay. So then we can see that this can be written as U at the diagram like this. So now I can call this my Heisenberg operator. So it's a more general definition of the Heisenberg operator in terms of time development operator. And if you now calculate the time derivative of this Heisenberg operator, you'll find that it also fulfills this different this equation of motion. Yes, as I have it in the notes. It's just some algebra. But anyway, in this case, we are talking about some time-independent Hamiltonian. So we do not need to worry about this one here. It's just a remark that it's a more general equation of motion here. Okay, so let me look at the time here. Okay, so maybe that's a good point to have a break before we continue with the next one on the Ehrenfest theorem. So, are there any questions?
I have a question.
Yes.
When you do the derivative of the Heisenberg operator, from that I assume that the exponentials commute with O.
No. So that's a good point. So the exponential does not commute with O. Yes. So you have to be careful here when you take derivatives. So first you have to take derivative with respect to this exponential, but the h can be put either in front of this or after. Yes, because h commutes with itself. So that's why I can write it like this. Yeah. And then I have to take the second derivative here. So that will bring down also h. But I can put it in front or after the exponential. So that's why I get h. Yes, because h commutes with itself.
Is this done in more detail in the notes?
Well, I mean, yes. I think you can see this in equation 2.31 in the notes.
Okay, thank you.
If you have, yeah. So basically, it's based on the fact that the h commutes with itself. So you can place the h either before the exponential or after. Yes. So in the first term here, I put the h in front. So then I'm left with OH. Because when I take derivative with respect to time, we will bring down the IH on each bar. So then I have exactly the same thing. So that is just OH. And then in the second term, I take the derivative with respect to this exponential.
Oh, okay. I see now.
Yeah, you see what I'm, yeah.
Yes.
Yeah.
Thank you.
Okay. Good. Are there any more questions? If not, then we meet again at 1:15. Okay, we can continue. So I would like to illustrate this, the use of this Heisenberg equation of motion to problems of just free particles. So this is related to what's called the Ehrenfest theorem. It's quite an interesting theorem, actually. Ehrenfest theorem. Okay, so let's consider free particle. So we can restrict ourselves to one dimension. So the extension to 3D is quite straightforward, I think. So we have a Hamiltonian free particle. So then that's just p squared upon 2m. So now we can use the Heisenberg equation of motion. Let's look at the momentum for the moment. So that's dp dt is equal to commutator of p with h. Finish the operator here. So that's of course is 0 because p commutes with itself. So that implies that the momentum is a constant of the motion. So that's good because it's you're looking at you're considering a free particle case, and then the momentum should be a constant of motion. So that's what we would expect. So more interesting is if we look at the equation of motion for the position operator. So that is equal to upon h bar like that. So that's x h according to the Heisenberg equation of motion. So this is then become what do we get here? Bar p squared. So in the appendix, I have a formula. So there's a general formula. So if you have a commutator of x with some function of operator p, so that is equal to h bar df dp, like that. So you can see the derivation in the appendix. I don't remember what the number of equation, the equation number, but you can easily find it in the appendix. So then we do that, we get what do we get here? So then we get 1 upon 2m. This IH disappear. Then we get 2p. So that becomes just p upon m, as we would expect. So it's a kind of velocity. So from the first equation, we know that the p is a constant of motion. So does not depend on time. So then we can integrate this readily. So then we get x as a function of time equal to, so I just integrate this, yes, integrate into time here like this. So then we get, so because I have to integrate here also, so maybe I can put the whole thing like this. So then we get the x operator as a function of time, that's 0. So integrate here from 0 to some t, plus the momentum, which is a constant, right, by m times t, like this. Now, the position operator, they at different times do not commute. Yes, so that's important to realize. So if I take xt x0 like that, that is not 0. So this is then equal to x0 plus p1mt commuting x0. So that one of course commute, but not this and this one. So that gives me minus h bar upon m t, because p and x equal to minus h bar. So if we look at the uncertainty relation, so we have a general uncertainty relation before. So let's let me write it down here. So they are doing some work down there with a pedestrian. So I hope it doesn't disturb with the background noise. B like that. Quote. This is what we derived before. Yes. When we do the minimum wave packet. So we just plug this in, and we take A to be the xt and B to be x0. Then we get delta xt squared delta x0 squared. Let me take, yes, so that's greater than 1/4. So that's just h bar squared t squared. From here we get 4m squared like that. So this equation tells us that delta x, this expectation value of delta x t squared increases with time. Yes. So this is just fixed, but it grows like t squared here. So if you have a particle localized, let's say, time t equal to 0, then we expect that it will kind of spread in time. Yes. If you have a free particle. So if I put a delta function, so I will well-defined position at some point, and we now have Hamiltonian, which is a free particle Hamiltonian. So this delta function is not an eigenstate Hamiltonian. Then this delta function will kind of spread with time. So the delta x squared, the expectation value of that will increase in time. So that expresses the fact that the delta function is not an eigenstate of the free particle Hamiltonian. Okay, so that's the case of the free particle. More interesting if we now introduce a potential. So we have Hamiltonian, so there's a more general case. Plus some potential, let's call it Vx like that. So now things are a bit more complicated because the momentum operator does not commute anymore with the Hamiltonian. So that gives me h bar p x like this. So p, of course, commute with a p squared. So now we use the general formula that I mentioned before. So this is a function of. I should have mentioned that there's a kind of complementary formula also. Yes. So then this is equal to. There's a minus sign, I think. Yes. So if I have it's not operator commutator of p with some function of x or x operator, then this is given by minus h bar df dx like this. So that can also be found in the appendix. So then you see that this becomes minus h bar dv x dx. So that is just then minus dvx dx. So it looks a bit like a classical result. This is like the force time derivative of the momentum, and that's the derivative minus derivative of the potential. So that's very much like in classical mechanics. Okay. So let's look at the position operator now. So we have dx dt. So that is equal to m. So that's exactly the same as we had before, because x, of course, commute with the v, as v is a function of x. Like that. So that's just a bit like also in classical mechanics, that you have velocity is equal to momentum divided by the mass. So mass and velocity is the momentum. So I put these two together, then we see that we have m d2 x dt squared is then equal to minus dv x dx like this. And if we take the expectation value of this equation in the Heisenberg state, because we are now working in the Heisenberg picture, so we take expectation value in the Heisenberg state, so that corresponds to the Schrödinger state at time t equal to 0. We then get, well, just take the expectation value of this, so then becomes t squared like that. It's equal to minus d dx of this value. So this result is usually called the Ehrenfest theorem. So it looks very much like Newton's equation of motion, but there is something a little bit subtle with this equation. So it looks very much like classical equation of motion, but there is some difference, because when we take the expectation value of the potential like that, that is different from the potential calculated with expectation value of the position. So this is not in general the same. So one example I have in the notes is if we take cubic, say, if this is equal to some cubic potential. Then we see that dv dx is equal to 3a x squared, like that. So then the expectation value of v x is equal to 3a x squared, like that. But if we take the expectation value of x instead, calculate the v, and then take the derivative, that gives us something equal to squared, like that. So there's a difference between this and this one here, which reflects the uncertainty in the position. So we have to be aware of the difference between this equation and the usual classical mechanics Newton's equation. Okay, so that's one kind of general example of the use of the Heisenberg equation of motion. And the next example, so let's consider another example. So look at the spin precession. Spin precession. So here we have a spin under some magnetic field. And we have some spin like this. So let's say the B is in the Z direction. So then the Hamiltonian is just given by minus omega. So omega is given by MC, like this. That's a rather simple Hamiltonian. So we will look at the Z component of the spin. Then of course this is 0 because the Hamiltonian is just given by Sz, so that is equal to 0. So it just means that the Z component is a constant of the motion, doesn't change with time, like one might expect. So it's more interesting to look at the other components. So let's look at the X component. Dx dt. So that then becomes minus omega upon h bar from the equation of motion x z. So we know from the angular momentum commutation relations that is equal to, okay, I forgot the h here. Okay, like that. So then this is equal to minus IH bar SY. So then we get omega SY. So I will look at the second derivative of this. So I can think of this as d dt of dsx dt. So that would be then 1 upon I h bar sx dt and Hamiltonian. So I treat this as the operator. But then we know that dsx dt is equal to omega sy. That becomes, if I use the h, that becomes minus omega squared h bar sy z. So this then becomes h bar is x. So then we get minus omega squared sx like that. But these are just equation of the harmonic oscillator. But for the operators, and if we take the expectation value, then we find the solution is given by some constant cosine omega t plus another constant times sine omega t. So that's the general solution of this harmonic oscillator problem. And we have to determine these coefficients a and b. And to do this, we need to decide what is the initial state, because it depends on the initial state at time t equal to 0. So this expectation value here, it's some initial, it's taken with respect to some initial state. So we take the initial state to be, let's say, what do I have in my notes here? Okay, so let's take the spin up. So the initial state is equal to the spin up. Is that direction? Then we can easily see that we calculate x 0. So that would be just 0 because it's equal to 0. We can check that. But if we look at the general solution, that would imply that a is equal to 0 because only the cosine survives. Sine omega t is equal to 0 is just 0. And if we look at the derivative calculated at time 0, so when we write it like this, sx ddt of sx0, we mean that we first take the derivatives and then calculate it at t equal to 0. This can kind of understood this. So that will then gives me the omega y0 from the previous result. And again, this thing is 0 because sine up is equal to 0. So that's equal to 0. So that would imply that b is equal to 0. So everything is 0, actually. That will again give me sx t is equal to 0. So it's kind of expected because the initial state is a spin up along the z direction. So the expectation value of the x and the y component will just 0 all the time. Yeah, it's nothing strange here. So, but the more interesting case perhaps is if we look at the case where we have the eigenstate of Sx. So we take our initial state here to be the eigenstate of Sx. So that will be plus spin down that. Then we get something more interesting because when we get x 0, so these are just the expectation value of the Sx in that state. So that gives me h bar upon 2. So let me write it down. So that is the so this here. So there's that one, and that state is this state here. So that gives me h bar upon 2. So then that gives me a equal to h bar upon 2. Whereas if we look at the derivatives of the x calculated at 0, that is equal to omega sy 0. So this thing here is the expectation value of sy on the initial state, psi 0, and the initial state is an eigenstate of x, so that is 0 then. So then we get 0, and that gives me b equal to 0. So we get the solution here. This function of time becomes just h bar upon 2 cosine omega t. So this is also kind of expected because we start with state which is an eigenstate of x, and it will just kind of rotate in this way. So the x component, this function of time, will rotate like a cosine, as the y component remains 0. And yeah, okay, so that's one simple example. Then if I have time here, yes, we can also do the harmonic oscillator. We have probably done this before, but we can do it. It's another illustration. So we take the harmonic oscillator. And this is just like that. And we can look at equation of motion for the position operator. So that gives me h like that. So that we have done this before. So that just becomes p upon m, because it commutes with the x squared, and x and p squared gives me to p divided by m. We look at the momentum. So that will then give me commutation with the x squared term. And if we use the general formula, we will get equal to x like that. So we take another derivatives of the position operator. That will give me 1 upon m dp dt from this one here. And so that then becomes minus x squared x. And similarly, we do it with a p, we'll get 2p dt squared equal to minus x squared p. So both x and p are obeys same kind of oscillator equation. And we know the general solution of this. So I call it A equals get t plus p sine I get t. And for the momentum, we get different constant. Let's see. Let's say d. And all these coefficients a, b, c, and d are determined from the boundary conditions. T equal to 0. So it's just some kind of, I think it is quite a straightforward algebra. I think I have this in my notes here. So you will find that A, so A is actually an operator here, is then equal to x0, and the B is equal to P0 divided by omega m. And C is equal to 0, whereas the D is equal to minus m omega x0. So those are these coefficients A, B, C, and D, which are operators. So we find the solutions. We just plug this into these equations. Yes. Okay. So those are two rather simple examples. Well, we did 3 actually. We did the Ehrenfest theorem and the spin precession and the harmonic oscillators. Okay, so I think we still have some remaining time here. So in the remaining time, I would like to start talking about the propagator. So this is very much related to the Feynman path integral. So we have our time evolution operator. Let me write this down again. T0, that's what we found. And with this time evolution operator, then we can determine the development of this of any state. So we start with any state and then we just evolve it. Just multiply this or operate it on some initial state and gives us the state at a later time t. So let's have a look at this operator in the position representation. So we want to calculate not the expectation value, but the matrix element of this in position eigenvectors. So let's call it xn, x0. So we want to look at the position representation of this operator. So we call this k. So xt, x0, t0, like that. We can also add theta function to indicate that the t is bigger than t0. This means that t is bigger than t0, otherwise it's 0. So that's just to indicate that we have an initial state at time t equal to 0, at time t equal to t0. So first of all, what does this mean here, this matrix element? So let's first try to understand the physical meaning of this matrix element. So we say that if we apply the time evolution operator to an arbitrary state, then it will give us the state at a later time t. So if we think of x0 state here as our initial state, 0. So we have a particle localized at position x0. So that's our initial state. Then the time evolution operator acting on x0 will give us the state at the later time t. Yes. So this is to be t0 here. So I should write t0. Okay. Okay. So then this matrix elements becomes x psi t, like that. So that tells me the probability amplitude of finding the, say, the particle, which is initially at x0, and to be found at position x at a later time t. So we can interpret this k xt x0 t0. Can interpret this as the probability amplitude it's important that it is probability amplitude of finding a particle initially localized at x0, at x, let's say, and time t. Initially localized at x0 at time t0. So we can think of it as probability amplitude. This thing's a little bit tricky because the position eigenvectors It's a delta function in position representation. So you cannot actually take the square of this, doesn't mean anything. You take the square of a delta function, and well, then it becomes infinite. So one should think of it as kind of relative probability amplitude, yes? Because this state is not well defined. The normalization of this state is not well defined when we have a position eigenstate. So we should, when we say probability amplitude, we should think of it more as a kind of relative probability amplitude, since you overlap in the state and the position eigenvector. Okay, so that's the meaning of this propagator. So this is called the propagator. Propagator. So we can also see why this is called the propagator if we go a little bit further. So that's equal to minus I h divided by h bar. So that is just psi t. Okay. So psi t0 is just some initial state. So this then is equal to, we insert complete set of states. I got it x0 in my notes. So this thing is just the k that we defined before. So then it becomes so I've included the definition of theta in the k. So this is just the wave function xt. So you can see that this object here is gonna propagates the wave function at x0 t0 to the wave function at x and t, and then you have to, of course, integrate over the x0. So we can work out the more explicit expressions for this propagator by inserting a complete set of the eigenstates of the Hamiltonian. So that's like what we said earlier. So I don't know, to check the time here. We have enough time today. So, okay, so maybe we should do this next time. So, yeah, already at 12 o'clock now. Okay, so maybe we should do this next time. So, are there any questions so far? I think most of you are already familiar with this Heisenberg equation motions. So, there is a question here. So why there is a theta function? So the theta function, as I said before, is there to make sure that the t, since the t here is bigger than t0, it's just the definition. So by having a theta function, then we are implying that we are looking at the later time, t which is bigger than t0, is the initial time. Here we are looking at the time development of the state at a later time. So are there any more questions? If not, then we can stop here and we see again next week. Okay. Goodbye for now.